Hi guys, welcome to one of the another sessions on estimations. So here we will talk about the linear models. Not just all linear models, but some of the most basic fundamental concepts related to linear models. So let's talk about ARMA models, auto-regressive moving average models. So these models are like a black box doing a lot of processing. So here we have our input xk, which is k, where k is the discrete time index, and they process and give the output yk. So yk is the output at kth time, and it depends on the past input as well as present input value and all the past output values. That is why it is called auto-regressive moving average. Looks like two things contributing to the output. So the first term is the summation m is equal to small m is equal to 0 to capital M, b of m, xk minus m. So if you see, xk is the present samples, input samples, xk minus m is a delayed past input samples, and we multiplied with some coefficients bm and start from 0. So it means we're using the m. We are using kth samples and m minus 1 earlier than k. And then we subtract n is equal to 1 to n, a n, yk minus n. So notice here the summation starts from n is equal to 1. It means the output at kth time instant depend on the output at k minus 1, k minus 2, and up to k minus n. It means only past outputs. And in terms of transfer functions, h of g, we know transfer function of this ARMA systems can be written as the g transform of output divided by g transform of input. And if we took the z transform on both sides and take the y to the right hand side, we see that y by x will become summation of m is equal to 0 to m bm z power minus m divided by 1 of yk plus summation n is equal to 1 to n e power n z of minus n. And this is a polynomial both in the denominator as well as numerator. You know that these polynomials could be solved to get the factors. So in the factors form, we can write h of g, the transfer function, is some constant bo into product of 1 to n z minus z0. And saying similarly, we have denominator as a product of several terms, g minus j, z infinite minus v. So these z0 comma mu and z infinite comma nu are all constant values, and they represent some point in the z plane. So there are two important quantities derived from this expression. If we make denominator equals to 0, or we make denominator equal to 0. So let's make numerator equal to 0. So for all the values of z0 comma mu, where mu could be 1 to m, we get different values of z, and those are known as zeros. So these are the points at which the transfer function is 0. Poles, on the other hand, are obtained by putting the denominator is equals to 0. So it means for all the value of z infinite comma nu, where nu could be from 1 to n, the denominator is 0 and the value of transfer function will be infinite. These are very helpful for commenting about the stability of the systems and are used in other purposes for system design, for example. And we will come back to poles and zeros concept. But it was just a quick refresher of the concept, how we get it. Now ARMA is one system where the output depends on the past output depends on the past input, both. So there could be some simplifications. For example, what will happen when the output only depends on the past input values? And such a system is known as the moving average. Moving average means all the past values are being averaged. Input values are being averaged to get the output. So here output is given as the weighted sum of the input and input values Vm x k minus 1. This is same as the earlier expressions with the output part omitted. And similarly, we have a complementary system which is known as auto-regression. So auto-regressive system is a all-pole model. So here we have the output at kth instant depends on the weighted sum of the output at all last n samples. And that's why, so this is a regressive model. So output at one instant is dependent on all the outputs, previous outputs, not all, but last n output values. And it has no dependence on the input. So we call it auto-regressive model. Definitely the ARMA model is a more general model and we rely on that more often. However, for some practical applications, these simplifications into moving average or auto-regressive is very helpful. Well, after this point, I talked mostly about the ARMA model and their simplifications. It would be interesting to understand the stepstone distance at this point. So stepstone distance measures the difference or similarity between two processes, X and Y. So if stepstone difference between two stochastic processes, X and Y, or two signals, X and Y, is smaller, we say they are similar. So here the assumption is that the similarity is measured only on the basis of spectral magnitude, not on the phase. So we assume that the spectrum of the signal X and Y, the only amplitude is taken into account for measuring similarity. And this is defined, stepstone distance is defined as the delta Cxy is in stepstone distance xy. Delta is like distance. And it's from k is equal to minus infinity to infinity. It is just a way of writing. In reality, we don't have infinite samples in any of them. So these are just some measurable. And we take the Cx of k, it means we have the autocorrelation function of the input vector x with itself. So autocorrelation function, covariance function of x with itself. And here the Cyy is the covariance of y at time k. And we take the successive time-wise subtraction and we square and add it. This is the concept of distance. In spectral domain, this is given by integral 1 by 2 pi. So 1 by 2 pi is a discrete angle. So we put 1 by 2 pi to normalize it, and then from minus infinity to infinity, d of omega. Again, I would like to say that the discrete angle omega is not going to vary from minus infinity to infinity. It is some smaller set to compute the integral on, and this is given as the difference of log of sxx. So this is the spectral density of x minus log of syy, which is power spectral density of yy. So we can either compute it using the power spectral density and the covariance. Well, it's also important to highlight that there is a unique correspondence between the power spectral density of a signal to its correlation function. The Fourier transform of the autocorrelation function is same as the power spectral density. That is how we see that these expressions are similar in some ways. So this was all for this episode, and we will return back with more concepts and explanations.